we'll cover the problem binary search on structy. This is a pretty classic algorithm, and you'll see it kind of underlies a common pattern that we can apply to a surprisingly diverse set of problems. With binary search, the core idea is that we can kind of, when searching for a number, we can cut the space that we're searching in half every time. So for example, if we have a sorted array, and note the inputs for this problem will be a sorted array of numbers and a target number. So here we're searching for 6. Now we could just iterate until we find 6, but we could also kind of find a strategy that cuts our search space in half repeatedly. So we could start at this middle element, for example, and we could say, all right, let's compare 4 to 6. 4 is less than 6. But because this is sorted, we know that everything to the left of 4 must also be less than 6. Therefore, we can cut out this entire search space, and we focus on this chunk. Then we grab the middle of this chunk. That could be 6 or 7 based on how you do it. I think most ways that people calculate it would result in 6. But for demonstration, let's just say it was 7. You look here, you say, these are my valid numbers. 7 is too big. That means everything to the right must be too big. So we can focus on this space. Then you grab the middle number, and now it would be 5. That's how most algorithms work. You check 5, it's too small. So this was your space before. Now you cut it in half, and you have 6, and you find your answer. And this is the idea for binary search. So we can go ahead and code this out. So the way we'll do this is we will have a left index, which starts at 0. And I'm actually just going to grab a quick constant for our last index just to make things a little bit nicer. Our right index is going to start at the last index. So we kind of have a pointer here and a pointer right here. Now we will go ahead and we're going to iterate so long as, how do we want to do this actually? Yeah, this is fine. We can do left index less than or equal to right index. And here we're going to grab our middle index. I'm going to write a function that does this for us because we could do it the way that you've probably seen before, which would be just kind of like add the numbers, divide by 2. But there is a better way to do it because if you have 2 really big numbers and then you add them together, that can cause some problems for the computer or based on the programming language, or it just has to store a lot of data that you're just going to cut in half anyway. So the way you can do this is you take the left number and then you get the difference between these 2 numbers and cut that in half. And then you add that to the left number. And that is equivalent to actually averaging the 2 numbers. Because you can kind of think of it as like, to get from left to right, you just add the difference. But if you took the difference and cut it in half, then that gets you halfway from left to right. So you're stuck in the middle. Okay, so we have our mid index here. So that's kind of like 4 initially. Then what we can do is grab our mid value, which is just going to be numbers at mid index. Here we'll say, first things first is if the mid value is our target, we're done. We don't have to do anything else. So we can return our mid index. Otherwise, if the mid value, I guess we can do else if the mid value is less than the target, right? So we're looking at 4. This is smaller than the target. Then we know that everything to our left is irrelevant. So let's just move our search space to look at this. So our left pointer is here and our right pointer is here. Our right pointer should stay the same because we still want, these elements over here to be in our search space. But our left pointer can come all the way up to 5 because we know 4 is not valid. So we'll say left index is going to equal mid index plus 1. And then the last case is going to look similar to this. Otherwise, if the number is greater, so say we're at 7, for example, then we want to move our search space to look at everything to the left that's still in our search space. So we take our right index, which could be, let's say, at 8, and we move it to the right of the mid index. So we'll say right index equals mid index minus 1, like so. Okay, so all of this should work. There is one case, which is that the target is not in the array. And if that happens, eventually these guys are going to cross each other because we keep increasing the left index and decreasing the right index. So if we never return something and we break out of the loop, it means that there was no target found. We could not find the target. And so here we want to return -1. We'll go ahead and create a constant for this just so it can be as readable as possible. And then here we'll return not found. So we can go ahead and run this and see if it works. Use the test command instead. Oops. Okay, great. So it looks like that passes. We don't need to do that. And one other point I want to make is the way this algorithm works is first we look at this search space. Then we cut it in half and we look at this search space. Then we cut it, well, actually we find the answer here, but conceptually we cut it in half to this search space and half to this search space. So we basically, first we have n elements, then we have n over 2, then n over 4, then n over 8, then n over 16, then n over 32, then n over 64, until we get down to 1 element. And so this process of where we just continuously divide by 2, it gives us log n time complexity, specifically log base 2 of n time complexity. And that is the advantage of binary search. Log n is a lot better than n when you start looking at very massive numbers like 10 million, 100 million, a billion. It is very helpful at that scale. All right, well, that's all for this video, and thank you for watching.